let me discuss this in a realistic scenario and give you a few hints now on linking this to real life. So here's an example of an actual transmission line, which I called before the microstrip line. It's probably the most common transmission line you will find out. It has this substrate, which is a dielectric material with a dielectric constant of epsilon r. It has a metallic ground on its backside. That's basically a metal that covers the entire bottom of the substrate, and then it has the signal strip, which propagates on another layer of metal. Usually that's copper, that has a particular width W. Usually the thickness of this thing is pretty small. Usually it is measured in the order of few micrometers. So for right now, we will assume it's perfectly planar, and we'll make this approximation. And then this substrate thickness is called H, and that H does have a significance, which we will see a little bit later on. Now, let's think intuitively of what happens here. So we just said that the impedance of this line will be equal to L by C, or it will be equal to 1 by CV. And so essentially what that means is that I can control this capacitance per unit length to basically change the impedance. So if I make this capacitance to be a large number, then as you can imagine, the impedance will be a low number. So that means that if I design this microstrip line here to have, this is a top view here. So if I can actually design this to be a fairly wide line, as you can imagine, I'm making the capacitance per unit length quite large, because that means that I have a higher overlap between the signal strip and the ground. And that means that this guy here will be a lower impedance than, for example, this guy here, which will be a higher impedance. So the first thing, and the reason I'm showing you this geometry, is because once you understand the basics, you can just literally look at the circuit and make very informed decision of what's happening there. So if you just look at the layout that you see here, you say, okay, somebody's trying to lower my impedance as they move from the left-hand side to the right-hand side. Why that might be the case, we'll discuss later on, but at least just by looking at this thing, you can actually know that pretty quickly. Now, there are other things that come into the design of this microstrip line, which I will discuss in a minute. One of them is probably quite important, is the epsilon r, is the dielectric constant, and of secondary effect is this H that you will see here. What I drew here, by the way, I didn't explicitly mention, is the electric field lines that will exist in this microstrip case. And as you can see, some of those electric field lines are completely inside the substrate, but some of them are actually in air. And that is the first hint, if you remember from your electromagnetic days, that this line cannot sustain a TEM mode. For a TEM mode, you need the fields to be in a uniform medium. This is not a uniform medium. Part of the field is in the substrate, part of the field is in air, which basically means that you don't have a pure TEM mode. But you have a quasi-TEM. That means close enough. And so we will approximate this as a TEM mode, but later on, probably on Friday, we'll have a little bit of time to give you some hints of where things break down if you truly take into account that this is not a pure TEM mode. So let me show you a few interesting graphs where we will be able to get even further insight on practical transmission lines. So these are two graphs that basically give you the impedance, C0, on the left-hand side, and the effective permittivity on the right-hand side. I will explain in a minute what is effective permittivity. But for right now, let's focus on the impedance. The impedance here is given in ohms. This is the characteristic impedance of the line, which is, again, is a number, simply divides the voltage by the current. In other words, it simply tells you how much current you have given the voltage. And that's the role of an impedance. And then on the on the horizontal axis, you have W by H, which essentially means how wide is your line. So for a given H, is it a narrow line or is it a wide line? So also there are multiple graphs for different dielectric constants, and these are dielectric constants that you can get in real life. Obviously, 1 is going to be approximately air, and over down to 40, which is a very high K dielectric. Most of practical cases, though, would be between 2 and 10. This is by far the most practical case. So notice, for example, that if your W by H is, let's say, between 1 and 3, then the first thing I'd like you to look at is that your impedances are going to be roughly between, let's say, 10 ohms, maybe somewhere down here, and maybe 100 ohms. So the first take-home lesson that I'd like you to know is that even though in theory you can design your transmission line in any length, any width, any thickness, and this is true for any transmission line, so even though in theory you can get any impedance you like, in real life impedances are going to vary typically in that range. Now you can push it to maybe get a transmission line with an impedance of 150 ohms, but if you go to industry and you ask somebody, can you please design me an impedance of 1 ohm or 500 ohms, you're risking losing your job, right? So that's not possible. Most of the times your impedance will be actually in that range. And that's true not just for microstrip line, it's true for most transmission lines. We'll discuss in a little bit next slide actually what happens if you really try to push that and where you're going to get severely penalized. But for right now, let's keep that in mind. Now let's shift our attention to the second graph. The second graph gives you effective permittivity, and what we mean by that is that because of the issue I mentioned last time in the last slide, that some of your lines, electric field lines, are in air and some are actually in the dielectric, we can replace this complex medium with just one effective medium that essentially contains the entire line. So here's my strip, here's my ground. So now everything here has one dielectric constant of epsilon effective. So in other words, the effective dielectric constant is an imaginary quantity that would be that would have the same effect if you were to put the entire electric field structure inside it, as it is in real life. So as you can probably imagine, the effective dielectric constant is going to be a number between 1 and epsilon r. Since you have one on one hand of the side, air, epsilon r is the dielectric constant that you have in the substrate. So the effective dielectric constant will be somewhere in between. And what this graph gives you is basically how much is this number. So again, it's a function of W by H. And so, for example, you can see that let's pick one of them. Let's pick epsilon r of 4. So if my epsilon r of 4, I'm basically looking at this line here. So if I'm looking at this line there, no matter how much W my H is, the effective dielectric constant is going to be approximately, let's say, 3. But if I take a more aggressive epsilon r, so let's say an epsilon r of 20, then if my W by H is a small number, I could be down to 12. Or if my W by H is a large number, I could maybe as high as 15 or 16. So you can basically see here that you can control that. And the reason that this is important to know is because now your capacitance per unit length is a direct function of the dielectric constant. And capacitance per unit length is critical not just because of impedance, but because of speed as well. So these are basically two interesting graphs to keep in mind because, again, very quickly, by just looking at the geometry, you can make a guess of where things are. Now, if you want to make an educated guess and you have nothing in front of you, you can make the zeroth order approximation that the dielectric constant, the effective, is 1 plus epsilon r by 2, meaning the average. But there are computer programs, as you will see from ADS, that can give you this number very quickly, or equations that are actually in the textbook that you can also program and get this thing very quickly. So in this last slide here for this topic, I'd like for us to focus on a few important trade-offs. So I already mentioned that you have some issues to worry about in terms of Z0, but let's see what happens if you try to make a line, for example, really wide or really narrow. Let's say you're trying to basically truly get to the ends of those trade-offs. So the first thing that I would like to basically say is that, of course, if you make a wide line, you will get a high capacitance per unit length, obviously. And if you get a high capacitance per unit length, you can actually expect two things. One is you will get a low impedance, as we just already saw. But another thing which we haven't discussed much yet is you will also get a low resistance. Why will you get a low resistance? Is because now you have basically a wider strip, and that means you lower the resistance of your line. And that's good. That means low loss. But if you try to push this to the extreme, if you try to make your transmission lines too wide, you'll have a few undesired effects. Let's list a few of them here. One is you risk higher order modes. As you can imagine, at some point, this thing would just look like a parallel plate capacitor. And so you're basically risking higher order modes. The second thing you're risking is radiation. Unfortunately, when you make something very, very wide, it actually tends to radiate. In fact, there is a very well-known antenna that looks exactly like that, and that's called a patch antenna. And so a patch antenna is a radiator, not a transmission line. So if you try to reduce the loss by making the line wider, you're basically risking radiation. And the last part you're risking is actually high cost. Why are you risking high cost? Because your size is huge. You're basically making everything really, really wide. In fact, today, we try to shrink interconnects as much as possible to reduce the capacitance per unit length because of speed. So not only you're risking high cost, but you're also risking, if you're doing a digital domain, low speed. Now, similar things happen on the other side, of course, if you try to make a transmission line narrow. Obviously, in this case, your capacitance per unit length will be low. That will actually bring you a lot of good advantages. First of all, it will bring you high impedance, which you may or may not like, depending on the design. But I would say this is a little bit of an indifferent point at this point. You will have several advantages. You will have, for example, the low size, which is good. High density of interconnects is also a good thing. But you will have, and I'm not going to list all of them, but you will have high loss. And high loss is a big deal because it also means dispersion, and it also means slow speed. So again, these trade-offs are important for you to realize because there is no optimal solution for anything. It always depends on what you're trying to design for. And as I mentioned before, even though it might look frustrating at first sight, this is also job security, because unless, if there was really a program that will give you everything immediately, you wouldn't be able to get, not many RF engineers will be needed.